Hello and welcome to another video. Today we're going to be continuing on with the Typescript line 75 and we're going to be doing maximum depth of binary tree. So in this problem, a binary tree's maximum depth is the number of nodes along the path from the root to the leaf, and you want to return the height, so the farthest leaf. And in most of these problems, height is calculated in a few ways. In some of them, they will say that like the height of this is actually 2 because the root node has 0 height. Sometimes the root node has 1 height. So in these cases, the root node has 1 height because if you have a tree like this is supposed to be 1 height in their example. And so how do we do this? And that part is pretty straightforward. Let's just say we have nodes. We don't really even care about the values, right? We don't care about the values at all. So I'm just going to draw a tree with no values. Obviously, they will have values, but we don't really care about them because they don't matter to solving this problem. So it's pretty straightforward how you do this. You just start at the root, and then you just recurse down. You either go left or right. Let's say we go left. And the default base case we're looking for is a null node. So for a null node, the height is going to be 0. So we can write that down. Null, height is 0. And then for a not null, the height will be the max of children heights plus 1, right? And let's see why that makes sense. Let's just go through this example and let's see why that makes sense. So for this node, they're going to have 2 null nodes, right? So the height of both children will be 0. So the max of the children heights will be 0. Then we're going to add 1 here. So the height of this node is 1. Now we recurse back up and we go over here. And then we go left first. So all these nodes with no children, their heights are always going to be 1, right? Because the heights of both children are 0, so plus 1. So this will be height, this will be 1, this will be 1. But yeah. So essentially now you return 1 up here, and this also returns 1 up here. And now remember, for a node, the height of it is the maximum of its children plus 1. So the maximum of its children is the maximum of 1 and 1, which is 1 plus 1, so this will be 2. And now this node, as you can see, it has 2 children. One of them has 2 height, one of them has 1 height. So it's the maximum of the children plus 1. So that'll be 2 plus 1, which would be 3. So a really straightforward algorithm. You essentially just recurse down until you hit null nodes. And then for every single node, you just take the maximum of children plus 1 because every time you add a node, you're increasing the height by 1. And that's pretty much all there is to it. And now we can code it up. And we are actually going to code this in a one-liner because, like I said, it's pretty straightforward. So we are going to do that. So let's try to focus on that. So remember, let's focus on, is the node null first, right? So we can just say root question mark. So if the root is not null, then this will be true. So how do we calculate the root? Well, like we said, it was 1 plus the max of the 2 children, right? So it's going to be the 2 children recursive functions. It's going to be max depth root dot left. And we actually screwed that up a bit. So this needs to be max depth like this. And we can have max depth of root.right, right? So we're essentially going to both of the children, getting the maximum, and adding 1. So that's going to be our recursive case where the node is not null. But what if the node is null? Well, that one is also straightforward, right? It's just going to be 0. And so we do need to return these things, so we have to do this. So now essentially, once again, let's go over this. Essentially, we're saying, okay, we're going to return something. If the root is not null, right, root question mark, if the root is not null, then we're going to do this side. And so that means we are going to recurse left and right, take the maximum value and add 1. And then if the root is null, we're going to come over here and we're going to turn 0 because the height of a null node is 0. And that's actually pretty much it for this problem. So let's try that. Okay. And as you can see, like I said, this is kind of inconsistent. It's all over the place. So if you just submit, it's like all the solutions are kind of close, so it's all over the place. But it's as efficient as you can get for this problem. And let's go over the time and space complexity for this one. So for the time, worst case scenario, we will have to loop through every single node, right? Or I guess any scenario, we have to loop through every single node. So on average, like pretty much every single time we do this, we have to loop through every single node. There is no way to end early. We are going to recurse all the way down. And so that's going to be O of n, where n is the number of nodes. And what about the space? So just as usual, we didn't make anything new, but as always, our tree can look like this, where our stack frames will just keep going and going and going, and we will only recurse out once we've traversed the entire tree, which means our recursive call stack will be n length, so the space will be n as well. And yeah, believe it or not, that's it for this problem, one of the easy problems. So hopefully you like this video, and if you did, please like it and subscribe to the channel. And I will see you in the next one. Thanks for watching.